Hi, good morning everybody. Today I am going to talk on kinetics of reactions which are occurring in solutions. So, before that let us have a recapitulation of what we have learned so far, or maybe in the last couple of classes. So, in our last class we have talked on a new topic, that is magnetokinetics, that is effect of external magnetic field on chemical reactions, and these chemical reactions are between radical spaces. Okay. So, what you did over there is, or what you have heard over there is that you generate radical spaces by using brief pulse of radiation, and that is your light source from laser source, or maybe using flashlight. You generate ensemble of radicals, I mean a collection of radicals, and that radicals undergo consecutive other reactions. Okay, one after another it will undergo reaction and produce the desired product. Okay. So, in that case we have seen that if we apply external magnetic field, depending on the spin orientation, that is relative spin orientation of the partners of a radical pair, that is a radical pair is consisting of a pair of radicals. Okay. It is unpaired spins. Okay. So, maybe both of them up, or maybe both of them down, maybe one up one down, like this. And I have shown using the vector atom model, I mean vector model for those spins, how singlet state or maybe how triplet state can be generated. Okay. So, singlet state is basically like this, and they are in true sense spin opposed. Like if this is your z direction, then spins are oriented like this exactly, and it is doing this precessional motion. So, these two spins having are maintaining a phase difference of phase angle of 180 degree with respect to one another. But for triplet state, the situation could be like this, could be like this, of course along this z axis, okay, or it could be like this. So, it is doing the precessional motion about the z axis, and in this case, in this last case, the difference in phase angle is 0. So, they are maintaining a 0 phase angle. So, this is also a part of your triplet state. So, triplet means 3 states. Okay. And if you apply an external magnetic field, what is happening, that you induce a transition between these states, that is singlet and triplet. And depending on the initial spin parentage, if the initial spin parentage is say triplet, that means either this or that, or maybe like this, one of these three could be a description of the triplet state. So, if you apply an external magnetic field, that removes the degeneracy between these 3 triplet levels. Okay. And therefore, 2/3 of the total triplet population cannot interconvert to singlet, that is possibility is reduced. Only T0 and S can do this interconversion. Okay. So, therefore, the ultimate result is that if it is the radical pair which is of triplet parentage, you will expect more of escape product. More of escape product means cage escape, that is you will get more free radicals. Okay. But if your radical pair is of singlet parentage, the moment it is generated, it will tend to pair up the spin. That is, pair up the spin means that will tend to form a bond. Okay, that is your recombination, radical pair recombination. Very fast recombination is going to take place when the radical pair is a singlet, is of singlet parentage, I mean singlet state, starting state is a singlet. Therefore, on application of an external magnetic field will block the interconversion between singlet and triplet. Therefore, more of singlet state will remain, and it will tend to this will tend to increase the recombination rate. Okay. So, that happened and that happens, and I gave typical examples like typical examples like using benzophenone or maybe benzyl, that is that these two molecules when are micellized in sodium rhodosial sulfate micelle, and then you shine the sample with laser pulse, then radical pairs are generated. One partner, one of these two radicals is from the ketyl radical, another is from is the micelle component, that is micelle transfers a hydrogen to this excited state triplet benzophenone or triplet benzyl. Okay. Therefore, in presence of external magnetic field, their dynamic behavior has been found to get altered. Okay. So, that means in this case we have given a demonstration that although it is known that in general that chemical reactions can be perturbed by various external factors, okay, like pressure, temperature. Means if you increase the pressure, what is going to happen, that the number of effective collisions are increased, that is collision frequency is increased, therefore reaction rate is enhanced. If you increase, I mean because of the increase of pressure, what is happening, that they are coming close and effective collisions are more. In the same way, when temperature is increased, number of molecules having the minimum amount of energy that is required for crossing the activation barrier is increased, and as a result of that reaction rate is increased. So, that is the general trend, and you can explain that behavior using Arrhenius equation that can nicely explain why with increase of temperature reaction rate is getting altered, and of course in a positive sense. Okay, so pressure, temperature, maybe volume can indeed affect the rate of chemical reaction. But the last example what we have given you, that is in the case of your spin chemistry, when you apply external magnetic field, okay, it has been found to increase or maybe alter. Sometime it is increased, maybe sometime this recombination is decreased. So, that means pressure, temperature, external factor like the external magnetic field. If we deal with magnetic systems, I mean paramagnetic system or spins, then you expect, and especially when you use the confined system like your radical pair is generated within the micellar cage, then this effect is very much enhanced. That is, you can indeed see it. There is another example, that formation of exciplex. Okay. So, if this exciplex is basically formation of excited state complex, and if that happens as a result of transfer of electron in the excited state, then it is again a case of radical pair formation. Okay. And in present and radical pair formation, so when this radical pair recombines, then you get some fluorescence. Okay. So, that is your exciplex emission, and if you increase or decrease the depending on if you increase or decrease the external magnetic field strength depending on whether it is a singlet one or it is a triplet exciplex, your intensity, that is fluorescence intensity, may get enhanced or maybe sometime should get reduced. So, that is also a case of observation of spin chemistry, that is effect of external magnetic field on exciplex luminescence. So, that is similar to this hydrogen atom transfer, that is as I talked about in case of benzophenone in SDS, and of course, it is done using the technique of laser flash photolysis. So, it is a clear demonstration that external magnetic field can influence this singlet triplet evolution interconversion, and thereby your reaction yield is altered. Okay. In the same way, other factors like say external factors like ionic strength, pH can indeed affect the chemical reaction rate. Okay. So, next what we are going to talk about is reactions in solution. Okay. So, solution reactions are very important, because if you think of reactions what you study in chemistry, in many cases you encounter solution phase reaction. Okay. Say hydrolysis of ester, okay, giving rise to acid. I mean, if it is an acid catalyzed reaction, then it will lead to acid and the alcohol. If it is a base catalyzed reaction, then you will get the salt of the corresponding acid. Okay. So, the point is and in the same way means there are other examples, many examples, plenty of examples of this solution phase reaction, as for example hydrolysis of Rx, that is alkyl halide, giving rise to alcohol. It is a nucleophilic displacement reaction that your nucleophile, maybe which hydroxide, okay, depending on the mechanism whether it is S1 or SN2. If it is SN1, then initially your carbocation is generated, and then this carbocation is attacked by your base, or maybe a backside attack for SN2 case of your nucleophile and displacing the halide ion from the other side. Okay. So, this is also another solution phase reaction. There are also plenty of reactions, maybe some these are organic reactions, maybe inorganic reactions of ions, those are very important. So, solution phase reaction is very important, and it is characteristically different, that if you think of gas phase reaction and if you think of solution phase reaction, okay, these two differ a lot. Okay. Because solution in solution phase, your reacting species, that is your maybe your molecule, maybe your ions are surrounded by solvent molecules. Okay. But in case of your gas phase, it is a rarefied situation, because it is a gas, therefore it is a very dilute, maybe some cases you can consider this to be a dilute case. I mean, dilute case means it behaves like a dilute solution, very dilute solution, that reacting molecules or atoms or species are far apart. Okay. And collision may be a mode for reaction to take place. Okay. So, for gas phase reaction they will collide, and then subsequent reaction will take place. Maybe a wall collision in some cases could be very important. So, technically there are lots of difference between solution phase and gas phase reactions. There are considerable differences between reactions in solution and in gas phase. Okay. In solution, the concept of individual collisions between reactant molecule is not meaningful. Reactant molecules interact with solvent molecules always, because it is always surrounded by solvent molecules. Suppose it is if you consider a reaction where there is some electrostatic contribution, that is, a reaction between ionic species. Okay. Ionic species means you have got, say, one plus component, one minus component, or maybe both minus or maybe both plus. So, what is happening that when they are coming close to each other, if they are of opposite, if they are oppositely charged, then they will be attracted. Okay. They will be attracted, like this. Okay. So, the closer, the more is the attraction, because this attraction or interaction is guided by Coulomb's law. Okay. But suppose if in between these two attracting molecules, solvent molecules enter, okay, and suppose the dielectric constant is high, then this will tend to, what is happening, that tend to solvate both the charges. Okay. Therefore, solvated ions will result, and in that case the isolated or unsolvated ions and a pair of solvated ions, they will interact differently. Okay. Therefore, interaction, if the interaction is occurring in a different extent, or maybe interaction is less or more, then of course the result is expected to be different. That is, interference of solvent molecules in between these two interacting ions. Or maybe suppose if you introduce a solution containing lots of ions, then those ions, other ions like maybe salts, these will tend to solvate, or maybe this charge or maybe other charge is surrounded by other ions, as a result of which the effective charge on this ion originally and that one originally will be altered, will be reduced. So, interaction is naturally less. Okay. Therefore, they are considerably different. Now, gas phase reaction, there is a random distribution of collisions between reactant molecules, and the collision does not affect the subsequent collision probability. Okay. So, random distribution of collisions between reactant molecule. Okay. So, it is distribution of collision occurs in a random fashion, and previous collision is not going to affect the later collision. So, there is no influence. Suppose right now a collision is happening, so that collision is not going to affect the next collision with this molecule and the other molecule. Okay. So, collisions are independently behaving. Solution phase, what is happening? It is of course different from gas phase, because it is your molecules, interacting entities are surrounded by solvent molecules. Okay. So, the situation is of course lot different compared to gas phase reaction, and gas phase reaction is sometimes very simple, but the moment solvent enters into, the complexity comes into action. Maybe solvent molecule helps in doing some kind of transfer of energy from one entity to another, or maybe transfer of one atom to the other. It may be acting as a mediator. Okay. So, if two solute molecules collide, it is probable that these will make numerous successive collisions before their separation. Okay. It is a probable situation. The liquid structure acts like a cage, and it can hold the reacting molecules in close proximity for a set of successive collisions. Okay. So, it is acting like a cage. So, once you put a molecule or an ensemble of molecule into solution, say in water, then water will tend to cage it. Okay. So, water molecules are in the cage, I mean the solute molecules are in the cage of water. Okay. So, it will tend to remain over there for considerable period of time. Okay. Because changing over from one case to another will require certain amount of energy, and that may not be available. So, therefore, that is why liquid structure acts like a cage, and it can hold the reacting molecules in close proximity. Say like a geminate recombination, as I talked about in the last lecture on magnetokinetics, that when you shine your sample with laser light, the radical pair is generated. I mean, benzoferin goes to the excited state singlet, triplet. This triplet abstracts a hydrogen from my cell, and immediately a radical pair is generated. Okay. And this radical pair so generated remains within one cage, which is called the geminate cage. I mean single cage, or that is called a geminate pair. I mean geminate pair of radicals. So, that means this radical pair is caged by the solvent, okay, or maybe caged by the micelle itself. Okay. So, these reacting molecules are held by the solvent cage, allowing successive collisions to take place, and maybe who knows that out of such successive collisions maybe one collision will be effective for the reaction to take place. So, in this way solution phase, that is solvent molecules, help in promoting the reaction. Okay. So, effect of solvent, what can be the role of solvent? So, effect of solvent can be chemical. Chemical effect means it may directly participate in the reaction. Say for example, if you add say water, okay, water with NaOH solid, then what is happening? Heat is generated, sodium plus gets solvated and OH minus also getting solvated. So, you generate NaOH equated, or maybe think of say a reducing agent or an agent which can abstract hydrogen from, I mean which can generate hydrogen from water, say for example hydrides, or maybe say you if you think of reaction of sodium with water. So, what is happening, that the moment you add sodium, or when the moment sodium touches water, it catches fire. So, that means NaOH is generated, and hydrogen is liberated. Okay. So, therefore, so the thing is that the water can itself act as your reactant, like say for example, say lithium aluminum hydride. If it comes in presence of water, then hydrogen is liberated, and of course lithium hydroxide, or say sodium hydride plus water. So, NaOH plus H2. So, that means water is acting as reactant. Okay. Or it may be physical. It may be physical means such chemical reactions may not take place. Na plus water. Okay. So, you may expect evolution of hydrogen. Okay. So, therefore, the point is it is a case where water is acting as a reactant. Okay. So, it can participate in chemical reaction directly. Okay. It may act as a reactant, or maybe in some cases the solvent may be catalyst. Okay. So, it is regenerated after the reaction. So, it may be catalyst, or it may be physical. I mean involvement is as a physical involvement by modifying the interaction of the reacting species. As I told you that the moment you add water, that the moment water is coming in between reacting species, then the interaction between these two entities will be altered. Okay. Solvating the various ions in the reaction in a different extent. So, lithium ion is getting solvated in a different way or in a different amount than sodium ion. So, it depends on the ionic potential. Okay. And it ensures a rapid energy transfer between reactant and solvent molecule. Okay. So, water, say it is providing a cage where intimate contact between the reacting molecules and the solvent will ensure the transfer of energy in between them and act to maintain the thermal equilibrium. So, it is acting as a bath, thermal, I mean maintaining a constant temperature. Okay. So, this sort of role solvent can perform. Okay. Now, diffusion controlled for diffusion controlled reactions, which I already have talked about in several occasions, that there is an upper limit to the rate of bimolecular reaction in solution. Okay. The rate with which two reactant molecules, say A and B, can come together is governed by the phenomenological laws of diffusion and of course conduction. Okay. So, it is guided by how easily they can diffuse. Okay. So, for a reaction to take place, they will have to come close. So, if other factors are not important, only this factor is important for the reaction to take place, then the rate is guided by this time required for these entities to come close via diffusion. Once the ions have come together, the encounter typically lasts approximately for about 10 to the power minus 11 second, and if the activation energy for the reaction is low, okay, it is the encounter frequency that will set an upper bound to the reaction rate. Okay. This frequency is in turn controlled by the process of diffusion and conduction that determine the rate with which the reactive molecules can get into the same solvent cage. Okay. So, therefore, this diffusion of the entities and their conduction is very important, and that can set an upper bound to the reaction rate. Okay. Now, many solution reactions can be depicted as follows. Okay. That is A plus B, A plus B, equilibrium K D, okay, and K B giving rise to AB, and then K2 products. So, this is your encounter complex. Encounter complex. Okay. Kb the unimolecular rate constant for the dissociation of the encounter complex. Okay. And if you apply a steady state treatment, then you end up with this rate law minus ddt of B is equal to K which is equal to K2 Kd divided by Kb plus K2. Okay. So, you have to apply steady state approximation onto this encounter complex. Okay. You have to apply. So, applying steady state approximation to this, what you get? This expression that it is a bimolecular, okay, bimolecular concentration of, it is dependent on the concentration of A and concentration on B. This is your overall rate, and this expression is this. So, only if K2 is much larger than Kb, okay, then the reaction is diffusion limited. Okay. If larger, then you can neglect this one and K2 gets cancelled. So, this is basically formation of your encounter complex. This is your diffusion rate Kd. Okay. So, that means if K2 Kd divided by Kb plus K2, if you write this to equal to K2 Kd divided by K2, that means this two gets K2 gets cancelled, then it is Kd. The reaction is said to be, the reaction rate is diffusion limited. For a slow reaction where, in other case, if a slow reaction where Kb is greater than K2, very greater than K2, slow reaction, why? Because this one is high, this back reaction is high, that is unimolecular decomposition of your encounter complex to give rise to A and B. Okay, for a slow reaction where Kb is very greater than K2, then your expression comes out to be equal to K2 Kd divided by Kb. So, what is Kd by Kb? Kd by Kb is nothing but your equilibrium constant. Okay. So, you can write K2 into K equilibrium. Okay. Where K equilibrium is Kd by Kb. AB is not a transition state, but it is a reaction intermediate. So, remember that AB is not a transition state, but a reaction intermediate. So, what you see that for a fast reaction, if it is forming the product very fast compared to the back reaction, compared to the dissociation of your encounter complex, okay, then this is a diffusion limited case. Okay, it is a diffusion limited reaction. So physically, that the moment these two entities, say these two entities are coming, okay, they will immediately do the reaction, giving rise to, say, product of this sort, or maybe say product of this sort. Say this is your product. Okay. So, that means these two steps, I mean consecutive steps Kd, K2, they are occurring very fast compared to the back reaction, that is Kb step, and under that situation you can call that this reaction to be diffusion limited. That is this is so fast, K2 is so fast that this is negligibly small, like your reaction between H plus and OH minus. The moment it is coming, generating your water, so there is no chance that the back reaction is taking place. Maybe water dissociates to form H plus and OH minus, but that is very small. So, that is why K2 is very high compared to Kb. But when opposite situation happens, then the reaction is it is a fast equilibrium, okay, followed by a slow decomposition of your encounter complex to produce your product. Okay. So, these two situations are different. In one case it is diffusion limited, in other case it is not a diffusion limited, but this is a fast equilibrium, quick equilibration between AB, I mean reactant, and your encounter complex. There is an equilibrium between them. Okay. Okay. Now, let us come to solvent exchange reaction. Okay. So, what is that? It is basically the exchange of solvent molecules between the primary solvation cell and the bulk solvent may be considered as the primary reaction of metal ions in solution. Okay. So, solvent exchange means your metal ion is there, it has got a primary solvation cell, okay, very close to your metal ion, primary solvation, and maybe bulk is somewhere here. So, these solvent molecules are considerably different than these molecules which are in the bulk, away from your charge. So, the exchange of the solvent molecules between primary solvation cell and the bulk solvent may be considered as the primary reaction of metal ions in solution. Okay. So, it is linked closely to the complex formation rates as well as playing a significant role in the mechanism of some redox reactions. Okay. So, why it is that? Because when complex is formed, then maybe these solvent molecules are replaced by the ligand, or maybe water can be a ligand as well. So, it is linked directly to the complex formation rates as well as playing a significant role in redox reactions. Redox reactions are nothing but electron transfer reaction, electron exchange reaction, where one oxidation state is getting converted to another, maybe say chromium 3 to say chromium 0, maybe iron to iron 3, nothing but this is nothing but the redox reaction. But these redox reactions are considerably affected, okay, in presence of solvated solvent molecules, that is solvent molecules which are surrounding your metal ion. Okay. So, there exists a very large range of first order rate constants for this process, varying from 10 to the power minus 7 to 10 to the power 10 for cations, and for anions this is almost invariably very fast, okay, that is 10 to the power 9 to 10 to the power 10 second inverse, it is close to diffusion limited. Okay. So, reaction is MH2ON, Z plus is the charge plus water. Water means this water is star means it is in the bulk water, okay, with a rate constant of K, giving rise to MH2O star H2N minus 1 Z plus water. So, this unstarred water is coming out. So, it is basically exchange of outer water going into inner primary solvation cell and the inner primary solvation cell water is going out. Okay, that is why MH2O, there are n number of waters in the in very close to M having Z plus charge on metal ion. So, it is solvent exchange, it is a typical solvent exchange reaction. Okay, and for cations it varies significantly from 10 to the power minus 7%, very slow, to 10 to the power 10, very fast for cations, and for anions the rate is almost invariably very fast, 10 to the power 9 to 10 to the power 10, this solvent exchange reaction. Okay. So, in this case the size of central atom is very important. The smaller the central atom, the more tightly the ligands are held. Other factors being equal, when you compare, then other factors should be unaltered, otherwise you cannot compare. The size of central atom is important, because if the size is high, then effective potential of that central atom will be less. So, therefore, soluble molecules are less tightly held, but for smaller central atom the more tightly the ligands are held. Okay. So, that is for water exchange rates, magnesium and calcium. Okay. See that for magnesium 2 plus it is 10 to the power 5, but for calcium it is 10 to the power 8. Okay. So, in case of magnesium, see it is rate is smaller, okay, but for calcium the rate is higher. So, you can correlate the statement that size of central atom is very important, and also charge is very important. Okay. So, sodium plus equated, for sodium plus equated you see charge is plus 1, and for calcium 2 plus the charge is 2 plus. So, the rate for sodium plus equated or hydrated sodium, it is 8 into 10 to the power 9 per second, but for calcium 2 plus it is 2 into 10 to the power 8, it is much less compared to sodium plus. So, charge is also important, and the size is also important. Okay. So, why I have told other factors being constant held equal, that means for magnesium it is 2 plus, calcium it is 2 plus. So, the charge factor is kept constant. Okay. Now, let us come to mechanisms of solvent exchange process. Okay. Now, these are special cases of nucleophilic substitution reaction of metal complexes, and the two end members are like as I explained over here, given over here. So, it is a dissociative mechanism. In this case, a transient intermediate of reduced coordination number is formed, that is the two end members, this is a reduced coordination state. Okay. So, this is one member, this is another member, and okay, water has been taken off. So, it is MlZ plus 6 ligands, then Ml5 same number of charge plus ligand, then adding another ligand, you are having 6 ligands. Of course, the other ligand is L primed. So, what is happening here, that you have got originally 6 water molecules, say, now this water is lost, giving rise to a 5 membered species. Okay. It is a square pyramid. Okay. It is an octahedral. It is an octahedral geometry, it is a square pyramid geometry. Okay. So, it is a dissociative mechanism, that this bond is dissociated. giving rise to this one. An associative mechanism, the other way. So, originally I mean previously it is dissociative, means you see that first the ligand gets dissociated and then this position is vacant, then the second ligand comes in. Okay. So, it is basically exchange of ligands. Okay. So, next case what is happening, it is an associative, means all the 6 ligands remain over there, then the 7th ligand comes in, okay, and coordination number increases from 6 to 7. Okay. So, it is a 5-membered plane. Okay. So, pentagon and pyramidal shape. So, it is an octahedron. Okay. So, you see that here ligand comes, it is producing like this, something like M L 5 L, then L primed, then maybe this bond is lengthened and this ligand is included in the activated complex. This is your activated complex. Then activated complex rearranges itself and releases this ligand, that is L. Now, what is happening? What has happened is M L primed L 5 Z plus. Okay, it is similar to SN2 kind of mechanism, that your the transition state, okay, is a, like say for your tetrahedral carbon atom, it is now becoming a 5-membered, I mean 5 coordinated species in the transition state, and then the 5th ligand is lost. But the dissociative mechanism is similar to your SN1, where the halide gets dissociated first, okay, giving rise to a carbocation, and then carbocation gets is attacked by your nucleophile. Okay. So, in an associative mechanism various possibilities exist. Okay. Considerable extension of the metal and leaving group bond, but very little interaction between metal and incoming group in the transition state is there. Okay. So, that means something of this sort may happen. Significant interaction between metal and the incoming group in the transition state, it may happen. There are various possibilities. Formation of a reaction intermediate rather than a transition state of increased coordination number. Okay. So, these are the possibilities for an associative mechanism. Okay. So, again if you go back to dissociative, you see ML6, ML5L. So, 6th position is vacant, ligand, I mean the second ligand L prime has the option to attack now. So, it attacks and giving rise to ML primed L5 Z plus charge. Okay. But here it is a little bit different than the earlier one, that this 6th ligand remains and then it leaves. So, this type of intermediate is a possibility, and then it rearranges itself in such a fashion that, I mean it rearranges itself and producing ML primed L5. Okay. So, these are the two situations, that is, one is associative, another is a dissociative mechanism for ligand exchange. Okay. Which of these mechanisms, how can we judge that whether it is an associative mechanism or a dissociative mechanism? Okay. Now, again you see that you have got, in this case your water is lost. So, you generate a species, single species to a double species, I mean this plus water, or maybe this plus ligand. In this case this plus ligand to a single species. So, 2 species forming a single species during activation process. Okay. So, let us look at the activation parameters. Activation parameters means, so initial state, this is your activated state, and then maybe somewhere here your product state, maybe here or here or here, whatever. So, like this, maybe, okay, this is your activated state, this is your initial state, and this is your final state. Okay. So, the expression is del ln k del T p, del T p of ln k is equal to E A by R T square, and del ln k del p T is equal to delta V by R T. So, this is energy of activation, this is volume of activation. Okay. So, what is happening here? So, when it is a case of associative mechanism, that means because of this activated state formation, I mean 2 to 1, there is a loss in entropy. So, entropy of activation will be less, entropy of activation will be less. Okay, I mean negative, in negative sense. But for if it is a dissociative, then you may expect entropy to be increased rather. Okay. So, therefore, just by looking at the delta S double dagger, delta S activation and its sign, magnitude and its sign, you can in principle judge whether it is a case of associative or it is a case of dissociative mechanism. Okay. So, delta V is also more useful for understanding the solvent exchange mechanism. This is a consequence of the fact that the incoming and outgoing groups are same and are unchanged. Thus, volume change of solvent can be neglected, and also delta V 0 for the overall reaction is 0, but in some cases that may also change. Okay. So, delta V double dagger is the volume of the transition state minus the volume delta V of the initial state. Okay. So, therefore, delta V double dagger is also useful, okay, in understanding, that is pressure dependence of ln k will give you the delta V. That will also give you the idea of whether it is an associative or it is a dissociative case. Okay. But when the incoming and outgoing groups are same, then it is difficult, I mean volume change can be neglected, but if these two are different, then you may not ignore it. So, I guess today I will have to stop over here, and maybe I will have to elaborate this delta V activation in the next lecture. But before that, let us sum up that we have talked about solvent exchange reaction, and it is the exchange of bulk solvent to your primary solvation, I mean primary solvation cell. It is the exchange of molecules which are in the primary solvation cell and in the bulk solvent. Okay. And how this is changing, the factors like charge and also the size is important, and mechanisms are like dissociative mechanism and could be an associative mechanism, and that can be well judged with thermodynamic parameters like these activation parameters. Okay. So, I guess today I will stop. So, in the next lecture I will talk on this delta V activation and also on the on the electron transfer reactions. So, till then, have nice time. Thank you.